Is time travel actually possible? 1. Introduction. Welcome to the Fact Factory, where we uncover the most mind-blowing mysteries of the universe. Today, we're diving deep into one of the most fascinating questions of all time. Is time travel actually possible? From Einstein's groundbreaking theories to mind-bending paradoxes, we'll explore the science, the speculation, and the strange possibilities that could turn time travel from fiction into reality. Can wormholes be our gateway to the past? Could advanced physics hold the key to jumping through time? Or are we trapped in the relentless march of the present? Get ready for a thrilling ride through space and time as we break down the real science behind time travel. If you love mind-expanding facts, don't forget to like, subscribe, and turn on the bell icon so you never miss an episode from the Fact Factory. Time travel has been a subject of human fascination for centuries, appearing in myths, literature, and modern science fiction. However, beyond fiction, the possibility of traveling through time has also intrigued scientists and philosophers. Advances in theoretical physics, especially in the fields of relativity and quantum mechanics, suggest that time travel may not be entirely impossible. This research explores the theoretical foundations, mechanisms, paradoxes, and experimental constraints related to time travel. 2. Theoretical foundations of time travel. The possibility of time travel is deeply rooted in the principles of Einstein's theories of relativity, which revolutionized our understanding of space and time. 2.1. Special relativity and time dilation. Albert Einstein's special theory of relativity, formulated in 1905, introduced the concept that time is relative and depends on the observer's frame of reference. A key implication of this theory is time dilation, which states that as an object moves closer to the speed of light, time slows down for that object relative to a stationary observer. This effect has been experimentally verified using synchronized atomic clocks placed on fast-moving aircraft, showing that time moves slower for the clocks on the aircraft compared to those on Earth. 2.2. General relativity and gravitational time dilation. In 1915, Einstein's general theory of relativity extended the concept of relativity to include gravity. It demonstrated that massive objects distort space-time, affecting the passage of time. This phenomenon, known as gravitational time dilation, means that time runs slower in stronger gravitational fields. Experiments have confirmed this effect using high-precision clocks placed at different altitudes, revealing measurable time differences based on gravitational potential. 3. Mechanisms proposed for time travel. Scientists have proposed several theoretical mechanisms that could allow for time travel, based on the principles of relativity and quantum physics. 3.1. Wormholes as potential time portals. Wormholes, or Einstein-Rosen bridges, are hypothetical structures that create shortcuts through space-time. If a wormhole could be stabilized and manipulated, it might allow for time travel between different points in time. However, their existence remains theoretical, and their stability would require exotic matter with negative energy density, which has not yet been observed. 3.2. Closed time-like curves, CTCs. Closed time-like curves, CTCs, are paths in space-time that return to their starting point, theoretically allowing an object to travel back in time. Some solutions to Einstein's field equations suggest that rotating black holes or cosmic strings might permit CTCs. However, the feasibility of such structures remains uncertain. 4. Paradoxes and challenges. Time travel to the past introduces paradoxes that challenge our understanding of causality and logical consistency. 4.1. The Grandfather Paradox. The Grandfather Paradox questions what happens if a time traveler were to alter past events, such as preventing their own grandfather from meeting their grandmother. If successful, the time traveler would never be born, raising logical contradictions. 4.2. The Bootstrap Paradox. The Bootstrap Paradox occurs when an object or information is sent back in time and becomes the reason for its own existence, creating a loop with no discernible origin. 5. Philosophical perspectives. Several philosophical interpretations attempt to resolve time travel paradoxes. 5.1. Novikov's self-consistency principle. The Novikov self-consistency principle suggests that any action taken by a time traveler was always part of history, thus avoiding paradoxes. 5.2. The chronology protection conjecture. Physicist Stephen Hawking proposed that the laws of physics prevent macroscopic time travel to preserve causality. 6. Quantum mechanics and time travel. Quantum physics presents intriguing possibilities for time travel. 6.1. Quantum entanglement and temporal correlations. Some interpretations of quantum mechanics suggest that entangled particles exhibit correlations that could imply non-linear time relationships. 6.2. The role of quantum gravity. A unified theory of quantum gravity might provide insights into the feasibility of time travel, but such a theory remains elusive. 7. Experimental evidence and technological constraints. While time travel remains theoretical, some experiments provide indirect evidence supporting its possibility. 7.1. Time dilation observations. High-energy particle accelerators demonstrate time dilation effects, where unstable particles moving at relativistic speeds experience extended lifetimes compared to stationary ones. 7.2. The feasibility of wormholes. Although wormholes are mathematically possible, their creation and stabilization remain beyond our current technological capabilities. 8. Other studies. Scientists don't think this conception is likely in the real world, but they also don't relegate time travel to the crackpot realm. In fact, the laws of physics might allow chronological hopping, but the devil is in the details. Time traveling to the near future is easy. You're doing it right now at a rate of 1 second per second, and physicists say that rate can change. According to Einstein's special theory of relativity, time's flow depends on how fast you're moving. The quicker you travel, the slower seconds pass. And according to Einstein's general theory of relativity, gravity also affects clocks. The more forceful the gravity nearby, the slower time goes. Near massive bodies, near the surface of neutron stars, or even at the surface of the Earth, although it's a tiny effect, time runs slower than it does far away, says Dave Goldberg, a cosmologist at Drexel University. If a person were to hang out near the edge of a black hole where gravity is prodigious, Goldberg says, only a few hours might pass for them, while 1,000 years went by for someone on Earth. If the person who was near the black hole returned to this planet, they would have effectively traveled to the future. That is a real effect, he says. That is completely uncontroversial. Going backward in time gets thorny, though, thornier than getting ripped to shreds inside a black hole. Scientists have come up with a few ways it might be possible, and they have been aware of time travel paradoxes in general relativity for decades. Fabio Costa, a physicist at the Nordic Institute for Theoretical Physics, notes that an early solution with time travel began with a scenario written in the 1920s. That idea involved massive long cylinder that spun fast in the manner of straw, rolled between your palms in that twisted space, time along with it. The understanding that this object could act as a time machine, allowing one to travel to the past, only happened in the 1970s, a few decades after scientists had discovered a phenomenon called closed time-like curves. A closed time-like curve describes the trajectory of a hypothetical observer that, while always traveling forward in time from their own perspective, at some point finds themselves at the same place in time where they started, creating a loop, Costa says. This is possible in a region of spacetime that, warped by gravity, loops into itself. Einstein read closed time-like curves and was very disturbed by this idea, he adds. The phenomenon nevertheless spurred later research. 8. Conclusion. While theoretical physics suggests that time travel may be possible under certain conditions, practical implementation remains a significant challenge. The existence of paradoxes, the need for exotic matter, and the unresolved nature of quantum gravity all present obstacles that must be overcome. Future advancements in physics may bring new insights, but for now, time travel remains an exciting possibility rather than a reality.